Keep me on the run here. I've never been on the straight and narrow, Ian. Okay, what does it mean to be a basis for a vector space W? It means that B is a linearly independent set and the span of B equals W. Those two things. Give an example of a linear transformation from 3 space to 2 space. We've had this problem before, but it means you have 3 domain variables because it begins in 3 space, but you only have 2 range variables. So this could be x1 plus x2 plus x3, and then comma, maybe 2x1 minus 3x2 plus 4x3. So there would be one. What does it mean for L from V to W to be a linear transformation? This means, you can say this in 2 ways. You can say there is a matrix M so that L of X is M times X. And the second thing you can say is that this is a 2-part thing. L of any U plus V, or X plus Y, is equal to L of U plus L of V. And B, L of any constant A times U is equal to A times L of U. So these two have some names, actually. And I don't think I've told you these names before, but the first one says that L respects addition. And the second one says L respects scalar multiplication. So L respects addition means this. L respects scalar multiplication means this. You can factor L inside the scalar multiplication. What is the row space of a matrix M? The row space of a matrix is the span of the rows, the row vectors of M. The span of the row vectors. The column space is the span of the columns of the column vectors. Number 7, what is the null space of a linear transformation? The null space of L equals all of the x's where L of x equals a 0 vector. The solution set of L of x equals 0. Here is the column space. What is the column space of M? This is the span of the column vectors of M. What is the range of the linear transformation? So the range of L equals all the vectors of the form L of x, where x is in the domain. And I specified the domain here, R3. So the range is all of the image vectors. These are in R4. What are all the possibilities for the geometry of subspaces of R3? There are 4 of them. The first one is the easiest one. It's just 0, 0, 0. And the last one is R3 itself. So those 2 are pretty easy. This is any line containing 0, 0, 0 is a subspace, and any plane containing 0, 0, 0. That's them. Lines to the origin, planes to the origin, or the whole space. All right. Page 1, we're out of here. But we have more on page 2. What does it mean for a set of vectors to be a subspace of R5?
Professor, I think you skipped 11.
Oh, yeah. If L is a linear transformation, what does it mean for a vector to be an eigenvector with eigenvalue 5? Vector V. So number 11, this means L of V is 5 times V. It's a constant times itself. And the constant is the eigenvalue. All right, number 12. What does it mean for a set of vectors to be a subspace? This means several things. X is part of R5. So every vector in X is a 5-dimensional vector. And that is obvious. It means that the 0 vector, I'll just write it 0 vector, is one of the vectors from X. So it has to have 0. And the other 2 are conditional. If X1 and X2 are members of X, then so is X1 plus X2. So if you add any 2 vectors from X, you get a vector from X. And lastly, if X comes from X, it's one of the things in X, and you take any real number A, then A times X is also an X. So you can multiply by scalars and keeps you an X. If you add any 2 things from X, it keeps you an X. 0 is in there, and X is part of R5. So these are the conditions. Number 13, what is the characteristic polynomial of a 2-by-2 matrix? So the characteristic polynomial of a 2-by-2 matrix, this is kind of the idea of how to find it. This is the determinant of A minus lambda times the identity. So this is the characteristic polynomial, just this. If you set this equal to 0, now it's called the characteristic equation. And if you remember that to be an equation, you've got to have an equal sign. That's how you can kind of tell the difference. If it's got an equal sign, it's called the characteristic equation. If it doesn't, it's called the characteristic polynomial. And you can tell what degree it is too. If A is 2 by 2, then this will be a degree 2 polynomial. If A is 3 by 3, it'll be cubic. If A is 4 by 4 matrix, then it'll be quartic and so on. But this white is the definition of characteristic polynomial. Where are we here? Number 14. If 2 is an eigenvalue of a matrix, what is the eigenspace? Ah, yes. This one is one I ask a lot. So the eigenspace E lambda equals 2 is the set of all vectors U or V or whatever, so that L of U is 2 times U. It's all the vectors that satisfy this. Or all the eigenvectors whose eigenvalue is 2. Those are the same thing. Number 15, if lambda equals 2 is an eigenvalue, what does it mean for the geometric multiplicity of lambda equal 2 to be 3? So this means the dimension of the eigenspace, so it was lambda 2, yep, is 3. Or there are 3 vectors in a basis for E lambda equals 2. Geometric multiplicity is 3, means that the dimension of the eigenspace is 3. What does it mean for B sub E to be an eigenvector basis? So this is the last one. So B sub E is an eigenvector basis for R3. If every vector in B sub E is an eigenvector, and B sub E is a basis for R3. So this is simply a basis consisting of eigenvectors. That's it. There are other ways to say this. You can say there are 3 linearly independent eigenvectors in B sub E, but that's equivalent to saying this, that this consists of eigenvectors and its basis. Questions on the definitions? All right. So let's rip into the non-definition part here. So the first question is to find the inverse of this matrix by hand. So we've got 7, 3, 2, 1. And you want to find the inverse by hand. So this is a by hand row reduction, beginning with the identity here in the matrix here. So here I would probably take -3 times row 2 and add to row 1 is my first step. So the second row will remain the same. And the first row changes. -3 times this plus this is 1. And that's why I did this. -3 times this plus this is 0. That was luck. -3 times this plus this is 1, -3. So that would be my first step. Now I would try to zero out this guy here. So I'd take -1 times row 1 and add to row 2. So the first row remains the same. The second row, this is 0, -2 times this plus this is 1, -2. -2 times this is 6 plus 1 is 7. And now we're done. This is reduced row echelon form. So M inverse is equal to this matrix 1 -3 -2, 7. And you can check that then with Mathematica. So this is the work that so in this problem, I'm not interested in the answer so much. You can find this with Mathematica, but I would be interested in the process here. So now in number 2, I give you a stochastic matrix and I give you the initial value and I want the third iterate, x3. So we take A times x0, that would give you x1. This would give you x2. This gives you x3. So we want to compute A cubed and then multiply by x0, and then that would give us the answer. And I think I did that on this Mathematica file. Here I checked in this problem 2, I checked the inverse by hand to make sure I had it right. Now here's the steady state stuff. So there is the matrix A. Mathematica doesn't like capital letters the best. It can mess up, it can conflict with their commands. So I usually use little letters for matrices or anything. So there is the matrix A. And then if I don't put this semicolon in, it'll just write it as a list. And then I wanted to look at the matrix form and so on. So let's blow up some of this stuff. There is the matrix A. There it is, the matrix form of A, which we didn't need actually, but now The next one is the matrix form of A cubed. So this is X3 right here. So there is the answer to X3. A cubed times that X0 matrix gives you this 0.0725 and then 0.0174 and finally 0.0491. So that is X3, which was the question I asked. And then I think the next question what do we do next? Oh, now the next question in that problem was, I don't think I have it here, but the next one was to find the steady state vectors. So the steady state vectors, I want to look at A minus the identity matrix. So A1 is that matrix, A minus the identity. Then I want to find the null space of that. You can do that in two ways. I row reduced it. And when I row reduced it, presumably this is the row reduction. No, that's not the row reduction yet. That's down here. So let's expand a few of these guys. So row reduced it, and that was this matrix. I didn't look at it in matrix form, but after we row reduced it, then these are equations. So we want to look at those equations. Row reduced A1. And let's look at the matrix form of that. So let's work with that matrix form. So this row reduced matrix is 1, 0, minus 1.3, let's say. 0, 1, minus 0.94. 0, 0, 0. So these are equations since we're looking for the null space. So this is x1 minus 1.3 x3 equals 0. x2 minus 0.94 x3 equals 0. And x3 is free. So the solution set x1 is 1.3 s. X2 is 0.94 s, and X3 is s, such that s is free variable, any real number. That's the solution set. And this is a collection of steady state vectors. This can be written as the span of just a single vector, 1.3, 0.94, 1. And so this is a basis. This is the steady state vector. And so this is the answer. The null space command, which I don't know if you've been using, but the null space command gives you a basis for the null space that you're looking for. So that last line there is an alternate basis for this vector space. And this is the span of 0.68 and almost 0.499, almost 0.5, and 0.53. And if you check it out, this vector is a multiple of this by just about 1/2, a little less than 1/2, a little more than 1/2. So these two are exactly the same. Both of these are steady state vectors. So that's it.
Professor?
Yeah.
I actually had a question on that.
Yeah, Ian.
If you add all three, aren't you supposed to get a total of 1? Not what you got, which was like 1.6, 1.7?
Oh, you mean right here, these three?
Yeah, like let's say you add all three together.
Yeah.
And then,
yeah, here the basis that the book has wanted, all of these are bases, but if we want these to be percentages, we've got to divide these. You are right. We've got to divide these by the sum. So this is 1.94 plus 1.3, 3.24. So the actual thing we want is probably 1.3 divided by 3.24, 0.94 divided by 3.24, and 1 divided by 3.24. These three will add up to 1.
okay, so then which one is the right answer?
So probably this one is the one we want right here. This single vector is the one we want right here.
Okay. And then I also had a question with the previous one, the one where you just find the state of x3.
Yep.
Aren't you supposed to do Mathematica matrix power?
Well, you could. I just did. You could use matrix power. You can, but I just used a cubed, and a cubed is the same.
I think I got a different answer when I did matrix power.
Oh, really?
Yeah. So I want to check that. And
yeah, let's check that out. What do you? So you did matrix power, and then did you put A and then 3? Is this the input?
Yep.
Yeah, and what matrix did you get here?
Let me do it real quick. I did it a while ago, so I'm just gonna do it real quick and see what I get.
When I multiplied that by x naught, got something like 0.39, 0.29, 0.3. That was my kind of x3 vector, I guess.
Same here.
Okay.
You mean for the last one, Asa?
For the one that's asking for the vector after 3 periods.
Oh, x3?
Yeah.
And what do you get here?
So my result when I multiplied kind of a to the 3 power times x naught was, the resulting vector was 0.397, 0.292, 0.309 approximately.
And this is not even close to what I got here. So I think A cubed, what I did was I used A cubed where A was a matrix. So I think this is bogus. So this matrix power, did you use the matrix power, Asa, or did you just multiply the matrix 3 times?
No, I used matrix. I said matrix power and then brackets A, comma 3, close brackets, period, X naught, close bracket. Or
Yeah. Matrix power A3 dot X naught, like this.
yeah, that's right. And then I did matrix form kind of around it all, but yeah.
Yeah, and then matrix form. I think this is the way to go. I didn't pay attention, but my answer is bogus. So I think this is
Yeah.
the way to go. I'll change that sheet.
I used that matrix power, but I got the same answer with you.
Oh shoot.
Yeah.
Professor,
Well-
I think since you did the A to the power of 3, didn't you say that for matrices we don't want to use that star multiplying sign? You want to actually do like the period?
Yeah, you want to use the period. So what we want
I
to
think
do
what, yeah.
is A dot A dot A dot X naught. This
I think, yeah.
this will work. The power of 3, I thought meant this, but apparently it
I
doesn't.
think, because I replaced your A to the power of 3 on your matrix form equation in the Mathematica, and I just did A dot A dot A, and I got that matrix that Ian was talking about.
Okay, I think this is likely right. So I'll change that Mathematica sheet probably tomorrow morning. So in mathematics notation, the A cubed is what it should be, A times A times A, but Mathematica sometimes changes notation on you. And looking at my answer, I think it cannot be, it is clearly bogus, I think.
Does A cubed in mathematical notation, does that just cube every entry in the matrix individually?
Oh, maybe it does. Maybe it does. It isn't what it means in mathematics, but it might be in Mathematica what it means. Let's stick with matrix power. I think that's a good idea. Let's move on a little bit. I think we're at problem 3. I give you a basis B1 for the plane and ask you for a change of basis matrix. And the change of basis matrix simply takes the basis that is given in order and puts those results in the columns. So this is the change of basis matrix from R2 with the basis B1, changes it to R2 with the standard basis. The next question is, what changes back? And that would be P inverse. And what I computed with for P inverse is 1/5, 2/5, 2/5 minus 1/5. So that changes back. Then in the second, this is the first part. Then in the second part, I give you something according to the basis B1. 3 minus 2. This is in the B1 notation. So that vector lives here on the left, and we want to change it here. We actually this is only a language change. The actual vector doesn't change, just the language. So what is this equal to in the standard basis? P takes you over. So you want to take P times 3 minus 2. And the result will be standard basis notation. So 1, 2 times this is minus 1. 2 minus 1 would be 6 plus 2 is 8. So I get minus 1, 8. So that vector in our language is minus 1, 8. That vector in B1 is 3 minus 2. And these are equal. Even though the numbers are completely different, they're equal as vectors. Then in number 3, we want to take 3 minus 2 in the standard and see what it is in the B1 notation. So 3 minus 2 standard equals what in the 1 notation? And P inverse is what does that. So if you take P inverse times 3 minus 2, you'll get 3/5 minus 4/5 is minus 1/5. And then 6/5 and 2/5 is 8/5. So again, these are actually equal as vectors. They are equal as vectors, but the language is different. So the basics of changing the basis. We good? Questions about this one? All right. So now number 4, I give you a linear transformation, ask you a few of the usual questions. So L is going to have as its domain R4, and it's going to map into how many little equations we have here, and we have 4 of them. And so the first, writing it as a matrix product here, the first one is 2, 1, 1, minus 1. So that this times this gives the very first row of L. Then 1, 2, 2, 1. The third equation is 0, 1, 2, 2. The last equation is 2, 3, 2, 0. So this is the matrix representation. So that is number 3. And this maps into 4-dimensional space since we have 4 rows or 4 equations there, 4 components. Number 4, find the range. So this is the first one we have to do a little work. And so the idea is that the range is spanned by these vectors. These are all range vectors. This is L of 1, 0, 0, 0, for example, the first column. So the range is spanned by the columns. The range is the same as the column space. And so there are 2 ways to do it. Method 1 of the book puts the range vectors that we have in rows. So 2, 1, 0, 2, 1, 2, 1, 3, 1, 2, 2, 2, and minus 1, 1, 2, 0. So it rearranged things. If this matrix is M, what we're looking at here is M transpose. And now it row reduces this. So we'll use Mathematica to row reduce. And row reduction will not change the fact that it only replaces these with linear combinations. So they remain in the same space, but the dependencies will show up when we row reduce. And I think when we row reduce, I get 1, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1 minus 1, 0, 0, 0, 0. So these are interpreted as vectors, and this shows up a dependency. So we have one dependency, 3 independent vectors, and these vectors are actually a basis, and they are a stepped basis. So this brings up the first basis for the range. So basis 1 for the range consists of those vectors, 1, 0, 0, 0, these rows, 0, 1, 0, 2, 0, 0, 1 minus 1, and that's it. Method 1. And there's a second method for finding the range. Are we good with this? I think I'm going to erase this and just work on method 2. So method 2 again uses row reduction, but it works it on the original matrix M. So 2, 1, 1 minus 1, 1, 2, 2, 1, 0, 1, 2, 2, 2, 3, 2, 0, reduced row echelon form. And this time we're looking for pivots. And I'm going to have to look on my sheet to see what we get. So I think when you row reduce M, I think this is what we get when we row reduce M. This time we're looking at pivots. We have 3 pivot positions. Here they are. This is not a pivot position because it doesn't have zeros to the left of it. So we have 3 pivot positions, and that tells us that the first 3 vectors, this one, and this one, the vectors, the original vectors corresponding to those first 3 columns are a basis. So a second basis selected from the initial range vectors that we had consists of just the first 3. This one is a linear combination. It doesn't tell you what it is easily enough, but it does tell you that only 3 of them are linearly independent. So method 2 gives you a second basis. Either one is a good answer to this question. 2102, 1213, and 1222. So what is the dimension of the range? The dimension of the range equals 3. This is the rank of the matrix M. And this says the range is a three-dimensional, 3D subspace of four-dimensional space. The codomain is R4. Questions about this? We good with this? Oh, I did say find the range, and I haven't written that down here. So I've found the bases for the range, but I haven't actually found the range yet. I'm going to erase these. I'm going to erase something maybe up here. And I should actually say what the range is. The range will be the span of any of these bases. So the range of L is the span, means all linear combinations of, and now you can choose either basis here.
Professor?
Yeah.
Are we going to have to announce which method we're using when we're finding the basis?
You don't. If you'd like to, it'll help me out. I'll follow your work in case you make a mistake, but that isn't part of the problem. The problem was just to find a basis.
Okay.
So we could use the stepped basis here, 1, 0, 0, 0, 0, 1, 0, 2, 0, 0, 1, minus 1. You know, I've taught linear algebra a lot, so lots have happened over the years, but it was several years ago. I had a guy, I mean, this guy ended up starting his own company. I don't know how much money he's made, but you know, it's more than double digits, let's say that. But in linear algebra, I would ask him to find a basis and he would find one that was just completely off the wall. It was correct, but he would use Mathematica and find some weird linear combination of these. So it took me forever to grade his exams. He would do such a thing on every problem. I would say, I wouldn't specify how to do it. I never do. But anyway, it was an interesting term for both of us, I think. The first time he did it, I marked a couple of them wrong and said, how the heck did you get this? Then he came in and pointed out they were right. All right, so enough of that. Let's take a look at the null space. We know that the null space now has dimension 1 because the sum of the dimensions is going to be dimension 4, the dimension of the domain. We already know that the rank is 3. So now we would like to find the null space of M, or the kernel of L. They're the same. And so in this case, what we want to do is solve M times X equal to 0. The null space is the solution space to this. So again, you want to take M and row reduce. You can think of M as being augmented with 0, a 0 column, or you can just remember this. And we know what the row reduction, we already did this row reduction. So here is the row reduction. But now we want to interpret these as equations. We're solving equations here. So this tells you that x1 minus x4 is 0, x2 is 0, x3 plus x4 is 0, and it tells you that x4 is a free variable. And So now you can write down what the null space is here. It's all the vectors x1, x2, x3, x4 satisfying these conditions. So x4 is S, x2 is 0, x3 is minus S, and x4 is our free variable S, such that S is any real number. There is the null space. Erase. All right. There is the null space, and you can write this as the span of just the single vector 1, 0, minus 1, 1. All linear combinations, we have only one free variable, so there's going to be only one vector in there. So the dimension of the null space of M is 1. So the null space is a line in four-dimensional space. And this is the basis right here. Basis is just a single vector, 1, 0, minus 1, 1. We good with this? Problem number last. So here I give you a matrix, and on the I put up, I think I already put this up on Moodle. I put up a new version of this where I put up a second matrix here, A and B. And these are similar, but I gave you A at first just to sort of check things out. So on this last problem, it should be problem 5. You're given this 3 by 3, 4 minus 3, 7, 0, 1, 1, minus 1, 1, minus 1. And I ask you to find the determinant. The determinant of A is 2. And this says the linear transformation represented by A doubles all volumes in this case, because this is a three-dimensional linear transformation. Find the eigenvalues. So used Mathematica, used eigensystem, the eigenvalues two, 1, and 1. This means that 1 is doubled. You can tell what the characteristic polynomial is here. The characteristic polynomial is this, and 1 occurs in 2 of these factors. And this is called the algebraic multiplicity of lambda is 1 because it appears twice. And if we look at the eigenspaces, E lambda equals 2 is the span. Now, 2 only has multiplicity algebraic multiplicity 1 here. So there is going to be an eigenvector. And in this case, it's 2 minus 1, 1. And the eigenspace for E lambda equals 1 is equal to the span of 1, 1, 0. So the geometric multiplicity of 1 is only 1. This is a dead end for us. So the next question, I think, says, I lost the next question. Is there an eigenvector basis in R3 corresponding to A? No, there is not. There are only 2 independent eigenvectors here. So the answer to number 5 is no. The matrix B can be written as, the matrix A can be written as A equals PDP inverse. What are PD and P inverse? No, it cannot. So it cannot be written as PDP inverse because the answer to the one before was no. And there is no blob diagram for it. So once we got here, this is a dead end. And we haven't run into these dead ends in class, but I put it here so that you see that it can happen, and here it happens.
So is multiplicity okay as long as one of the eigenvectors is not 0?
The 0 is not really an eigenvector. Mathematica puts it in there to tell you there isn't a second one.
Right, I see. Okay.
So let me just say that on the one that I put up, I give you a second matrix B, and I think I have B on this sheet here. Yeah. And B looks very much the same. Minus 3, 1, 2, minus 4, 2, 2, minus 8, 2, 5. So going through this, same thing for this matrix. If you do the same work, you find the determinant of B is equal to 2. So B also doubles all volumes. The linear transformation associated with B doubles all volumes. And the eigenvalues for B are 2, 1, 1. Exactly the same. But now the eigenspaces for B, the eigenspace lambda equals 2 is the span of a single vector, 1, 1, 2, and the eigenspace for lambda equals 1 is the span of 1, 0, 2 and 1, 4, 0. So B looks pretty much the same up until here. And up until here, now you do have 3 linearly independent eigenvectors. So now the rest of the program goes through. Now for this, you can create an eigenvector basis, and you can find the PDP inverse for this and draw the blob diagram. So I put this on here to kind of show you that things can look very, very similar. You can't tell until you actually do the work what's going to happen. A and B look very much the same until you get to this eigenspace thing. And the geometric multiplicity for B is 2, and for A was only 1. When you get only 1 in this case, it's a dead end. This is sort of what you meant, wasn't it, Asa?
Yes, thank you. Yeah, because I wasn't sure when I was going over it, if you could still, because I've seen, I feel like we've had situations where there's a zero vector in the diagonal matrix, or I should say there's a column of zeros.
No,
You're wrong about that. Anyway,
yeah, I think that should not happen.
that's not okay. Good to know. Thank you.
Yep. So that's about it. I will change the one on the stochastic matrix. That was my bad. And I'll make sure I'll put up a kind of a copy of the paper copy that I have of the exam. I'll put that up, and probably it'll be up tomorrow morning. So that's about it, you guys. I'm feeling like maybe I would like to call it quits. What do you think?
I thought a quick question for the